Okay, now that you've watched the videos um, uh, from, what is it called? Um, from IB Vodcasting. Oh my gosh, they're so good, and he explains it so well, and he's so calm in his explanations. Um, so you should be comfortable with the phase portrait introduction that he talks about, and being able to uh, deal with the saddle point, stable, and unstable examples. And so now I'm going to go over the homework, the back final pages of our assignment here. So the very first thing I'm going to do is I'm going to write my, we're going to try to solve the eigenvalues. So the first thing I'm going to do is I'm going to write this as 2, 2, 5, negative 1. I'm just taking these coefficients. Okay. Okay, so the first thing we're going to do is find eigenvalues. Okay. Okay, so to do that, I'm going to take the 2 minus lambda, and then put this 2 here, and put the 5 here, and negative 1 minus lambda. And we're going to find the determinant in order to and make this equal to 0. Okay, so now we're going to find our determinant. So once again, we do these two times each other. So we do 2 minus lambda times negative 1 minus lambda minus 5 times 2. And that's going to give me 0 in order to find our eigenvalues. Okay, and so this simplifies when 2 times negative 1 is negative 2. 2 times negative 2 lambda. That times that is plus lambda. And that times that is plus lambda squared, and then minus 10. Okay, let's combine like terms. And I've got lambda squared minus lambda and minus 12 equals 0. Okay, now I have to do some factoring. What two things multiply to give me 12 and subtract to give me 1? And it's going to be 3 and 4. Okay, and since this is negative lambda, the 4 here is going to be negative, and this is going to be positive. So now I've got my eigenvectors, my eigenvalues, and my eigenvalues are negative 3 and 4. So those are my eigenvalues. Okay, so I'm going to use these eigenvalues in order to find my eigenvectors. So for the first one, for the first eigenvalue with lambda 1 equaling negative 3, I'm going to put this into my matrix here. So I've got 2 minus, instead of lambda, I'm going to put negative 3, and then a 2, and then a 5 here, and then negative 1 minus, instead of lambda, I'm going to write negative 3, and then x and y, and equals 0 and 0. Okay, so let's simplify this here. Okay, 2 minus negative 3, that's going to give me 5, 2, 5. Negative 1 minus negative 3, so that's going to be negative 1 plus 3, which gives me 2. And notice I get the same thing, so I know I've been doing this right. So now I can write this as 5x plus 2y equals 0. Okay, so let's solve for x and y. Let's subtract 2y on both sides. I have 5x equals negative 2y. And so basically, when x equals negative 2, we know that y is going to equal to 5. Okay, hit pause anytime you need to think about this. So the eigenvector is going to be equal to negative 2 and 5. Okay, so this is the eigenvector that goes with lambda 1. Okay, and we're getting all these values, and we're going to be putting it into this format. So just keeping that in mind. Okay. Okay, so now for eigenvalue lambda 2 equals 4, now I'm going to say, okay, we're going to replace lambda with 4, so now I'm going to rewrite 2 minus 4, and then write a 2 here, and then write a 5 here, and negative 1 minus 4, okay, then x and y equals 0 and 0. Okay, so let's simplify it. 2 minus 4, that gives me 2. Negative 1 and negative 4 gives me negative 5. Oh, did I make a mistake? Oh, 2 minus 4, that should be negative 2. Okay, good. Whew. These rows should be equivalent, and if they're not, then you've made a boo-boo. Okay, so let's just take this top row. So negative 2x plus 2y equals 0. So now let's simplify this. I end up with 2x equals 2y if I add 2x on both sides. And basically, when x equals 1, y is going to be equal to 1. So I know my eigenvector, I'm going to call it p subscript 2, is equal to 1, 1. So I'm going to just do some color coding here. So when eigenvalue is negative 3, my eigenvector is that. And with the eigenvalue 4, I'm going to have an eigenvector of 1, 1. Okay, so using this relationship that we have down here, I'm going to replace the lambda 1 and the lambda 2 and the p1 and p2. And now I'm going to write my general formula. X equals a e to the power of negative 3t times negative 2, 5 plus b e to the power of lambda 2, which is 4, t, and my eigenvector is 1, 1. And this is my general solution. Okay. Alrighty, so now let's find a particular solution. Let's solve for the A and solve for the B at a particular point, and then we'll be able to draw our phase portrait. once we have that. So if you have had a little bit of difficulty following this, or you maybe I skipped a step and you're not really sure what I did, then you really should need to watch the earlier videos that I asked you to watch, because it really Pablo Sanchez is his name. He really does a very, very good job explaining this. You need to watch his videos. Okay, so now we're going to find our particular solution. So we're going to start off with a e to the negative 3t negative 2 5 plus b e to the 4t 1 1. Okay, so I've got my eigenvalues of negative 3 and 4 and my eigenvectors right here. Okay, so when t equals 0, let's just do one row at a time. So let's just do x. So when t equals 0. So when t equals 0, my x value is negative 6 equals a e to the, okay, now t is 0. So negative 3 times 0, this is still e to the 0, right? And then since I'm dealing with the x values, I'm only looking at the top thing, which is negative 2, plus b e to the 0. And once again, I'm dealing with x, I'm only looking at the top thing, which is 1. And so we can simplify this a little bit, and that gives me negative 6 equals negative 2a plus b. Okay. Now, for y, when t equals 0, the y value is 22, so I've got 22 equals a e to the 0 times 5, because we're solving for y, and the y value is 5, plus b e to the 0, and the y value here is 1. Okay, so let's make this look a little prettier. We've got 22 equals 5a plus b. Okay, so now we're going to solve for a and b. So to do that, I'm going to line them up. I'm going to write 22 equals 5a plus b, and I'm going to write, I'm going to change the signs of everything so I can add these rows together. So I'm going to change this to a positive 6, change this to a positive 2a, and then change this to a negative b. So what did I do? I just took this equation and wrote it down and changed the signs of everything. 6, 2a, negative b. And I did that so I can use elimination. Okay, I'm using elimination, and so then I can add these together. B and negative b, that goes away. 5a and 2a gives me 7a. 22 and 6 gives me 28. Okay, so if I divide both sides by 7, a equals 4. Okay, so now we solve for b. I can take either equation. Let's pick this one here. 22 minus 5 times 4 plus, wait, sorry, 22 equals 5 times 4. I'm replacing a with 4, and then plus b. And now we're going to solve for b. So 22 equals 20 plus b. Subtract 20 on both sides. B equals 2. So now that I know my a and the b, I can rewrite the general equation and I can write a particular solution. Particular solution is going to give me um, x, y equals, so a is 4, so I'm going to write it as 4 e to the negative 3t, negative 2 and 5, plus, instead of writing b, I'm going to say 2 e to the 4t, 1, 1. So all I did was rewrite the general solution, but now I have my A and my B. Okay, so let's draw the phase portrait for this. Okay, so what we've got here, so we know that they're going to both go through the origin, and so this one right here, if I go negative 2, okay, so I'm going to, in the x direction, I'm going to go negative 2, and then in the y direction, I'm going to go up 5. 1, 2, 3, 4, 5. Okay, so, and then 2 and 5. So I'm going to go like this. Okay. We're going to talk about which direction, where the arrows are going in just a minute, but there's my line. This is my line, negative 2x equals 5y. So I could really write this as y equals, and my slope is negative negative 5 over 2x. Negative 5 over 2x. Okay. Let's not write it like that. That looks confusing. So my slope is negative 5 over 2. My rise was 5. My run's negative 2. Okay. So now the other equation is I go over 1, up 1, over 1, up 1. So I can draw this line here, and this is y equals x. Oh, I shouldn't have put those arrows. We don't know where we're going yet. Okay. Okay, so now we need to think about when t goes to infinity. When t goes to infinity, this is going to get bigger, right? And this, oh, it's negative power, right? So if t goes into infinity, I'm going to have e to a negative number. This is going to get small. Okay, so as t goes to infinity, this is going to get bigger, this is going to get smaller. So our arrows for the getting smaller one are going to go closer and closer to the origin. Okay, the arrows, the blue line, where it's getting bigger, it's going to go away from the origin. Okay, oops, yeah, going away from the origin, going to the origin. And so now if I want to draw some trajectory points, I'll just put a random one here. It's gonna do this type of travel, and these, the blue lines and the yellow lines are asymptotes, so it's not going to cross the asymptotes. So it's going to go this direction. It's going to go like this. Okay. Draw some extra arrows on it just so you know where you're going. So here, it's going to go like this. Okay, and when you see something that looks like this is called a saddle point. And, you know, so it's like this example here. Okay. that's it for that first question. And that took a while, didn't it? All right, so so the next question, I want you to try this on your own. If you hit pause right now, you should try it on your own. And now I'm going to show the steps. But I'm not going to walk you through it. I'm just going to show the steps here. Okay, so I've rewritten this with my matrix and the x and y. I've found my eigenvalues to be 1 and 3. Using the eigenvalue of 1 and using the eigenvalue of 3, I go through the steps and I find the eigenvector of 1, 0. Using eigenvalue 3, I end up with an eigenvector of 1, 1. So then my general solution is this. Okay. Now find a particular solution. Now I'm going to rewrite this because it was so messy on my paper. Okay. So to find the particular solution on the previous page, right? And okay, so eigenvalue of 1 gave us this eigenvector. Eigenvalue of 3 gave me this eigenvector. Okay, now we're going to find a particular solution. So when t equals 0, we end up with 3 equals a e to the 0 times 1 plus b e to the 0 times 1. Okay, that simplifies to 3 equals a plus b. All right. And now when t equals 0, to solve for y, we've got 1 equals a e to the 0 times 0 plus b e to the 0 times 1. This is for y. This is for x. Okay. This simplifies to 1 equals, well, that's gone. 1 equals b. Well, that's easy. 1 equals b. So now we can solve for a now. So a plus 1. So that means a has to equal 2, right? So now we can write our particular solution. And our particular solution is xy equals, and I'm just going to rewrite this here, except my a is 2. 2 e to the t 1, 0 plus, and b is 1, so e 3 to the t 1, 1. And there is my particular solution. Okay, so so now we want to draw this. So this line here when x equals 1, y equals 0. So the slope on this one is 0, isn't it? So that, and all of them go through the origin, so that line is y equals 0. Okay, and the slope on this one, when x equals 1, y equals 1. So that's going to give me the line, why am I putting arrows yet? This gives us the line y equals x. Okay. Now, to figure out our arrows, we need to think about when t goes to infinity. So when t goes to infinity, this gets big, and this gets big. Okay. So the arrows are going away from the origin. Okay. So no matter where you are, it's going away. But notice this is 3 and this is just 1. So it's going to be going away, but it's going to be going away but more towards the blue one. It's not going to equally go away symmetrical like in this little picture. Not that one. It's not going to be perfectly symmetrical going equally away symmetrically. It's going to go away, but kind of go towards the blue one. It's going to, so this is going to go away and kind of go towards the blue one. This is going to go away and then aim towards the blue one. Going away from the origin and then aiming towards the blue one. Going away but aiming towards the blue one. Here. Okay, so it has that kind of a spiral, but you can see that it's always going away. And so if we looked at our naming scheme here, this is called an unstable fixed phase portrait. Phase portrait that's unstable and fixed. And the last question, if you're watching this in 2024, it's scratched out. New students it won't be scratched out for this. And so we go through this. My eigenvalues are 2 and -5. So when the eigenvalue is 2, we find out that our eigenvector is 2, 1. When our eigenvalue is -5, we find out our eigenvector is -1, 3. And so now I can write my general solution when my eigenvalue is 2. We've got that eigenvector. When my eigenvalue is -5, we got this eigenvector. There's my general solution. And then when t is 0, I make x equal to 1, and plugged in 2 here, and plug in -1 here. And when we're solving for y, we can make, this equal to 11 equals A. I'm going to put that with 1, B, and I'm going to put this 3 here. And then I can solve for the solutions, and then here if I go over in the x direction, I go over 2 and I go up 1, my slope is 1/2. Here if I go to the left 1 and up 3, you can see my slope is -3. And notice this gets small as t goes to infinity. This gets small and this gets big. So if this is getting big, I'm going away from the origin. If this gets small, we're going towards the origin, and then it helps me draw my arrows. I know this is a big assignment, but it's very important for understanding this chapter, and we need to know this before we go to complex eigenvalues and eigenvectors. And when we do that, that's when we get to understanding the spiral ones.